Hi, and welcome back. So in this video, we continue the study of logistic regression. So just where we ended up in the previous video, right, we introduced logistic regression, where the idea is that we would like to train still a linear model such that a hypothesis is specified by a vector W, and then we make predictions by computing this so-called sigmoid function of the inner product between W and X. And the sigmoid function here, this whole thing evaluates to 1 over 1 plus e to the minus inner product between W and X. And the intention is that this should equal the probability of seeing the label 1 given the feature vector x. That's the intention of what we would like to predict. And what we did then in the previous video is that we tried to define the likelihood of the data that we've seen. So if we've collected data elements x1 to xn with labels y1 to yn, then we said that the likelihood of seeing these labels for a given hypothesis w would just be, because the samples are independent, it's the product over all the examples of the probability of seeing the given labels given these feature vectors and this model W. And we argued that each of these individual terms just evaluated to 1 over 1 plus e to the minus yi inner product between W and xi. Right, so this is the likelihood of seeing these data labels. And then the intention of the idea is that we would like to choose the W, the hypothesis that maximizes the likelihood of seeing this training data. So we really want to return the W star that maximizes the probability of seeing S given W and X, which means we have to maximize this expression down here by choosing W appropriately. Okay, so we'll try to see how we can do this. Right, so there are a couple of issues with this compared to what we've seen before. In the previous videos with linear regression, logistic regressions, and decision trees, and so on, what we did was we studied minimizing a loss function, whereas here we're trying to just maximize a likelihood. So it's a little different. It's not a major issue. It'll be easy to deal with. Well, the second and maybe more serious thing is that this product that we have up here, it looks annoying when we want to maximize something. At least for all the other losses that we've seen, like the least squared loss and the 0,1 loss, we're really just summing over all the data points of some point-wise loss function, like the 0,1 loss on a single data point, or the least squared loss on a single data point. So in that sense, it's also different. Okay, so right, for 0,1 loss, this was the ensemble error for the perceptron learning algorithm. Just average over all the training examples. You count whether the hyperplane that you found, specified by W, misclassifies the point xi, yi. And again, for least squared regression, the loss that we're minimizing is the average over all the training examples of this squared loss, the difference between the prediction and the true label. It looks very different in this product up here. So to try and see how we can actually deal with this product, we'll try to study maximum likelihood estimates in a simpler setup. So this will kind of serve as a detour towards deriving the final loss function for logistic regression. The rest of this video will be dedicated to this detour and try to motivate the final loss function for logistic regression and how we can maximize a likelihood like this. Okay, so let's look at a different example that is simpler to deal with than the full general case. So let's say we have a biased coin, meaning that it has two outcomes, a heads, which you think of as a 1, and a tails with its -1. And the coin is biased, meaning that it's not uniform random between heads and tails, but it's equal to heads with some probability alpha, right? So we don't know alpha, and this is what we'd like to try and learn. Okay, now the training data that we have available for trying to predict alpha is the outcome of n independent flips with a coin, right? So basically here we're trying to predict the probability of seeing a heads, right? So it's very similar to the setup before with learning, where we're trying to predict the probability. The training data here is the outcome of n independent flips with the coin, again, similar to n independent training examples from this unknown distribution D. So each of these coin flips is either heads or tails. Okay. Now, the maximum likelihood model is, so what is the analogy of doing this maximum likelihood, taking this approach in the case of the biased coin? So in the case of the biased coin, right, the model really is just one parameter W, and we would like, at least that the intention is we would like this W to equal approximate the probability of seeing a heads, which is this alpha. So somehow this is the intention. We would like W, the one single parameter that we need to pick, to approximate this unknown probability of seeing a heads. Okay, so to try and see how we can actually do this, let's say that there's a beta fraction of all the training examples that come out heads. Okay, so beta might not necessarily equal alpha just because of sort of random fluctuations, but we know based on this Höfting bound, for instance, that we saw in previous lectures, that the more data I have, this beta is going to tend to alpha. Like it's going to get closer and closer to alpha as we have more and more data with high probabilities at least. And in particular, the expected fraction of points that come out, or coin tosses that come out heads, is exactly equal to alpha. Okay. So with this notion of alpha, we have this one model parameter W, and now doing the same as we did for logistic regression, let's try to pretend that for a given parameter W, this W was actually the true probability of seeing a heads. Right, this is similar to what we did before. We assumed that this inner product, as the sigmoid applied to the inner product, was actually the true probability of seeing the label 1. So here we assume, let's say that this parameter W that we picked was actually the true probability of seeing a heads. What would then be the likelihood of the training data that we have, right? So given that we believe that this is the right model, that this is the true probability of a heads, what would be the likelihood of seeing these n outcomes that we saw? Okay, so the fraction of ones is beta. So basically, right, the actual probability of seeing these outcomes is, well, so all the coin tosses are independent, right? And whenever we see a heads, given this model, right, the probability of seeing that heads would be W. And similarly, the probability of seeing each of the tails would be 1 minus W. So the likelihood of seeing this data is just the product over all the elements where we see a heads of W times the product over all the elements where we see a tail of 1 minus W. Okay, so really there's a beta fraction that are heads, right? So we get W raised to the beta n. And then we get a 1 minus W raised to the 1 minus beta n, right? This is exactly the likelihood of seeing the data. This is completely analogous to what we did for logistic regression. Good. So the maximum likelihood approach now would be to choose the W star that maximizes the likelihood of seeing this data, right? So the W star that maximizes this probability up here. Okay, so how can we choose a W to maximize this expression? Okay, so that's what we'll try to study now. This is because this is similar to what we want to achieve for logistic regression. Again, we have a similar issues as we had in logistic regression, namely that there's some exponentiations of a lot of products in this expression. So it looks a little bit annoying. So what we can do now to get rid of this is a nice trick. Instead of maximizing this product, we're going to minimize what we call the negative log likelihood. So what is that? So what we can do now is that we can just take this probability that we'd like to maximize and then take the natural logarithm and negate it, right? So what happens then to the expression? So if we do this, we take negative log of this whole probability up here. And the nice thing is, of course, with logs of products splits into a sum, and also the exponents move down, right? So what happens here is, so there's a common exponent n on all of the terms, so that exponent we can pull out. We also have the minus, and then inside here we have the W to the beta if we pulled out the n, so the beta moves down, and then we have log W. Similarly, if we have 1 minus W to the 1 minus beta, if we already pulled out the n, the 1 minus beta moves down, and then we have log of 1 minus W. Okay. So, so the reason why we're doing this is, so of course it simplifies the expression a lot, right? We get rid of all the products. Now, the log function is strictly increasing for non-negative x. So minus log is strictly decreasing for non-negative x, which really means that if I just maximize, if I want to maximize the original expression, then maximizing over x is the same as minimizing this negative log likelihood, right? Because the negative log function is strictly decreasing. Okay, so if I want to maximize x, it's the same as minimizing the negative log of x, at least for non-negative x. And so this is what we'll try to be using, that instead of maximizing this expression here at the top, we can just minimize this expression down here where we took the negative log. Okay, so taking log is a good idea, right? Because it gets rid of all these products. Negating, Well, so far it's not so clear why we're negating. We could also just choose to maximize without negating, just taking log and maximizing. But at least there's a good reason why, and in particular, if we would like to eventually to turn the logistic regression into a general loss function where we're minimizing something, it makes sense to turn it into a minimization problem. So we'll see why. Okay, so we need to choose W to minimize this expression now. That's the same as maximizing the original likelihood. Okay, so this here is a function of a single variable W, right? So it's a function from R to R, and let's assume this function is differentiable. Then in particular, if we want to minimize it, this is similar to what we did for linear regression, right? If we want to find the minimum, it must have a derivative of 0 in this minimum. But so the gradient really has to be 0 here, and the minimum of the function. So, but of course, right, the issue is that you could also have local maxima and saddle points, right? So we can have all of these three situations here where the derivative gradient is 0. Okay, so we don't know which one it is, but at least if we find a minimum, then it must have a gradient of 0. So that's the first kind of observation, and that we'll be building on. So what we'll try to aim for is that we have this function up here, and we'll somehow be computing derivatives and trying to set them to 0 in order to minimize this expression. Now, the really nice thing that we'll try to study more in this part of the video is that if a function is what we call convex, then there can only be one local minima and no local maxima and no saddle points, right? Which means the local minimum has to be a global minimum, and it's the only place where the gradient is 0, which means that then you'll actually get the exact global minimum. You'll minimize the expression simply by setting the gradient to 0. Right? So this is what this is the basic idea. For of course, right, what is a convex function? Right? So convex functions really only have one minima and no local maxima and no saddle points. So if I want to minimize a convex function that is differentiable, then I can just compute the derivative and set it to 0. That's the strategy that we'll try to follow. Okay, but first, of course, to do this, we need to understand what are convex functions so that we can check whether a given function is convex. Okay, so a convex function, a function is convex if the following holds. So a function is convex, a function L is convex in an interval from A to B. So you can talk about it, about a function being convex in an interval if the following holds. So for any 2 points, X and Y in the interval, right? So the interval is from here from A to B. If I pick any 2 points, say X and Y, and then the following must hold for every T between 0 and 1. So then here's a complicated expression. So let's try to see if we can pass it. So on the left-hand side, we have the function evaluated at T times X plus 1 minus T times Y. And that should be less than or equal to T times L of X plus 1 minus T times L of Y. So let's try to get an intuition for what this is saying. So let's try to just plug in T equals a half and look at what the inner expression in here on the left-hand side. So if I plug in T equals a half, then we get X half over here and Y half over here. So this is going to be exactly in the middle between X and Y. Similarly, if I put T to be a quarter, then I have a quarter X and 3/4 Y, and this is going to be 3/4 in between X and Y. Right. So basically this T here is going to interpolate between X and Y. In one end, when I set T to 0, I have a Y, and if I have T to 1, I have an X. So I'm kind of, this T is sliding between X and Y. Okay, so it's kind of saying that for all places in between X and Y, this is how this should be interpreted. Right, what is this expression over here? Right, this is just giving us the function evaluated at this interpolation point. Right, so I've interpolated maybe midways between it, and now this L of this point is just the evaluation of the function in this place. On the right-hand side, on the other hand, we're really interpolating between the function values at X and the function value at Y. So if you think about it, if we evaluate here in the middle at T equals a half, we get midways between the two function values. This is exactly the same as the midpoint on this line segment that you draw between X and Y. So the right-hand side here is really giving points on this line segment between the function evaluated at X and the function evaluated at Y. So what we're saying here is that the left-hand side is saying the function value at this interpolation point. The right-hand side is giving the value of the line segment between x and y at this point. And so the equality is saying that the function has to be below the line segment. That's exactly what it's saying, right? It's saying that for any 2 points, x and y in this interval, if I look at the line segment between the function at those 2 points, that has to lie above the function in between those 2 points. Okay, so that is the definition of a convex function. So, right, as you can see here, here's another choice of x and y, and you can see that the line segment indeed lies above the function. Similarly here, right, it lies above the function, and the function is convex between a and b if and only if this is true for all choices of x and y in this interval. Okay, you can generalize this to functions of multiple variables. Okay, so a function of multiple variables is convex in a set x, where x is a convex set, so we'll return to what that means, if the following holds, right? So x and y now are 2 points on the convex set. So the convex set now, remember, right, here we're talking about functions of multiple variables, right? So the convex set, so each of x and y should be thought of as a multidimensional point, right? So it's a multidimensional point. And what this is saying is really, if I pick, so on the left-hand side, again, I have the function evaluated on the line segment in between on the interpolation between the 2 points x and y. So I pick 2 points on the function, and then or I evaluate the function in between 2 points in this convex set. Sorry, so you pick 2 points in the convex set, you evaluate the function somewhere, all the places in between, and for all those places in between, the function has to lie below the line segment between the function evaluated x and the function evaluated at y. Okay, so it's just a generalization where you're saying that you can pick 2 points on the surface of the function, and then if you draw the line segment between those points, it has to lie above the function itself. Okay, and again, here we have a region x, and we say that this has to be a convex set. So let's just see what that means. Well, a convex set, if I have d dimensions, so I have a subset x of Rd, then this x is a convex set. If it holds that for any 2 points inside the set, and for any interpolation between them, so if I walk from one point to the other, then this point in between, so I'm just walking from x to y, this also has to lie inside the convex set. So all it's really saying is, if I have a set x is convex, if for any 2 points inside the set, the line segment between them, everything on the line segment also lies inside the set. Right, so that's the case over here. It's the case here. If I pick any 2 points in here, the line segment lies inside the set. Whereas for this heart here, the line segment between these 2 points does not lie inside the set, so this is not a convex set. So really what you should think of for this example up here is just the reason why I guess we would constrain x to be a convex set is that this point when we're walking between x and y, so this point over here where we're evaluating the function, all this is really giving us is that this point also lies inside the set x. Okay, so a function again is really of multiple variables, it's a convex function if I take 2 points on the graph of the function and I draw the line segment between them, then this line segment has to lie above the function itself. Then it's a convex function. Okay, and this also generalizes to functions of multiple variables, that if the function is convex, then there's only one minima and there's no local maxima and no saddle points, which means that you can minimize convex functions of multiple variables if they're differentiable simply by computing the gradient vector. In this case, this is what we saw last time. It has an entry, it has the gradient vector, right? It has one entry for each of the variables that goes into the function. Each of the entries contains the partial derivatives of the function with respect to each of these variables, right? So this gradient vector, we have to set that to 0, and that will give us a local minima, which is also a global minima by these properties. Okay, so of course, okay, so now we have a definition of whether a function is convex. So of course we have to check how can we determine if a given function is convex. Okay, now of course you can check that this definition applies, and you can just try to use a brute force and try to argue that indeed all these properties are satisfied. There are other different definitions that you could also find useful, and maybe for the different applications, some of these definitions are easier to use than others. Okay. So another definition that actually turns out to be equivalent to the first definition here is the following. And it says that L is a convex function in a set X, where X is a convex set, if again, for all 2 points, X and Y in the set, the following has to hold. So what does this say? It says that the function evaluated at Y has to be at least the function evaluated at X times the gradient of the function at X inner product with Y minus X. Okay, so let's try to see if we can get an interpretation of this, a natural interpretation. Okay, so let's go to one variable again. Okay, so what does it say? So again, it's convex between A and B, so we have this region that we're testing convexity in. If L of Y is at least L of X times, so the gradient, if I have just a single variable, is just the derivative of this function L at X times Y minus X. So what is this expression? It's a natural interpretation, right? So we have an X, we have a Y. What is this saying? So what I have over here, what I drew in blue here, I claim that this is really equivalent to the right-hand side. So what's happening here, right? So L prime of X, right? This is it's the derivative of X of the function at X, right? So the derivative of a function of a single variable is just the slope of this tangent that passes through the function at X. Right? So I draw the tangent that passes through the function at X. So this is this point here. So L prime of X is the derivative of, or is the slope of this tangent. And now what we're seeing over here on the right is now, so L of X, I basically means that I start at the value of the function here at X. And then what I add is, well, the slope of this tangent vector plus the distance out to Y. So this right-hand side is really evaluating to the tangent, what the tangent is at Y, right? So the right-hand side here is the value of the tangent that passes through X when you evaluate it at Y. So it's this point down here. Okay, what we have on the left side is, of course, the function evaluated at Y. So this is this value up here. And what this is saying is that for any 2x and y in the interval from A to B, if I draw the tangent through the function at X, this tangent has to lie below, when you go to the place, if you go out to Y, it has to lie below the function at Y. The basis is just saying that the tangent through any X has to lie below the function, right? Or so, the contrapositive is that the function lies above all of its tangents, right? So I can draw the tangent through any point and it has to lie below the function. Okay, so this is these are two equivalent definitions. And if you go to more general, to higher dimensions, this is just saying that the tangent hyperplane also lies below the function. Okay, so these are two different equivalent definitions. And maybe they're not the easiest to test. And there's another definition here that you can use if you have just a single variable. This one can also be generalized to multiple variables. We will not do it in this, at least in this video here. Okay, so the last definition that we'll look at is, at least if we have just a single variable, then we can say that a function is convex if for all x in the interval, the second derivative of the function at x is non-negative. And this is a fairly easy property to test for most functions of a single variable. I just have to compute this double derivative and argue that it's non-negative. Okay, so let's return to our example with coin tossing. So, right, we had this experiment, right, where we toss a coin. We say that an outcome of 1 corresponds to heads and an outcome of -1 corresponds to tails, and that there was a fraction of beta once in these n independent tosses. And then what we would like to do is to say, okay, let's assume that we have a parameter w, and let's assume that this w actually was equal to the probability of heads. If that was the case, then what would be the likelihood of seeing these outcomes that we have? Again, we argued that this had to be, well, the number of heads. You take the probability of heads, raise it to the number of heads, and then the number of tails. We take the probability of tails, raise it to the number of tails. We wanted to do the maximum likelihood, right? We wanted to choose the W star that maximizes this expression. And we argued that we could take the negative log instead and minimize that. So we took negative log of this probability, giving us this expression down here, right? -n times is beta log w plus 1 minus beta log 1 minus w. Okay. So now we're minimizing a function of a single variable w. Now, to minimize such a function, it would be really nice if this function turned out to be a convex function, right? Because then we could minimize it simply by computing the derivative and setting it to 0, right? So maybe let's try to see if we're in luck and that this function is a convex function. And for this, we'll use the third of these rules that we have. And then maybe one thing to be aware of here is that we have to choose w between 0 and 1, right? We're estimating a probability, right? So really it should be enough to show that the function is convex between 0 and 1, and then at least try to find a place where the gradient is 0 between 0 and 1. Okay. So we need to test for convexity, right? And there were several different ways of doing it, right? One of them is to test that all the tangents lie below the function. One of them was to say that the line segment between any two points on the function lie above the function, and so on. But here we'll use this last of the 3 different tests, namely the one that says that this function L up here is convex between 0 and 1 if for every w between 0 and 1, the second derivative of this function is non-negative. Okay, so this gives us a straightforward way to try and do the test. We just have to compute the second derivative of this one. Okay. And for this expression here, we'll again be using the chain rule, which says that, well, if I have a composite function, h being f of g of x, then the derivative of h is just the derivative of f applied to g of x times the derivative of g of x. Oh. So let's try to do this. So we want to compute the derivative of this function here. Okay, so it's a function of w, right? So minus n is just a constant, beta is just a constant. So we need to compute the derivative of the natural logarithm of w. The derivative of the natural logarithm of w is just 1 over w, so we plug that in. That was simple. The second here, this is a composite function, like 1 minus beta is just a constant. The composite function here, the outer function is log x, and the inner function is 1 minus w. So we have to, the derivative of the outer function is, if it's log x, it's 1 over x. So we have to take the derivative of the outer function, apply it to the inner function. So we get 1 over, and then we take the inner function, 1 minus w. Then we have to multiply with the derivative of the inner function. The inner function is 1 minus w. The derivative here is minus 1, right? Because the constant on w is minus 1. So this gives us a minus in here. Okay, so this is now the derivative of this function up here. Now we need to get the second derivative. So let's try to do that. So we do one more step of taking derivatives. So again, the minus n is a constant, the beta is a constant. The derivative of 1 over w is minus 1 over w squared. And so this is what we get here. And okay, so the minus here is just a constant factor, so we keep the minus. Then we need to take the derivative of this. The 1 minus beta is a constant. Now the outer function is 1 over x, right? So using the chain rule, we have to replace that by minus 1 over x squared. And then we have to replace this inner function with 1 minus w. So basically we get minus 1 over the inner function squared, so which is minus 1 over 1 minus w squared. Finally, we need to multiply with the derivative of the inner function. The inner function is again 1 minus w, so its derivative is minus 1. So we multiply it with that here. Because now we have an expression with a lot of minuses that kind of some of them cancel out, flip back and forth. And if we simplify it, we'll just see that, okay, there are 2 minuses here in the first term, so that just becomes a plus. And on the second term, there's a minus, there's a minus, there's a minus, there's a minus. So there are 4 minuses, it becomes a plus. And so this is the second derivative. Okay, so now we have an expression for the second derivative. And now we need to test that this is non-negative, right? At least between 0 and 1. But actually, if we stare at this expression as a function of w, right, we know beta is the fraction of heads, right? So beta lies between 0 and 1. So both of these numerators are non-negative. Okay, n is non-negative. And down here in the denominators, we have an expression that's w squared. And over here, we have 1 minus w squared. So both of these are squares of some numbers. So actually, regardless of whether this happened to be positive or negative, this is a non-negative number. So everything in this expression is non-negative. So this is a non-negative expression for all w. So indeed, this is a convex function, actually not just between 0 and 1, but actually in the whole, for all real numbers. Okay, so that's great. We've tested that this expression here is convex. So what we can do now is to minimize it is to set the derivative to 0. Okay, so all terms are positive here. Good. So we have to set it to 0, right? And we knew, so we have to set the derivative to 0, and we just computed before that this is the derivative. So let's try to set this to 0. Well, the first thing we can do is to multiply with minus n on both sides, right? So the minus n times 0 is just 0. And over here, it simplifies to beta over w minus 1 minus beta over 1 minus w. So what we get here is then we move the 1 minus beta over 1 minus w to the other side. So now we have 1 minus beta over 1 minus w should be equal to beta over w. And we multiply over the w, we divide by the 1 minus beta. So we get 1 w over 1 minus w should be equal to beta over 1 minus beta. I guess here I'm assuming that the numbers are non-zero just for simplicity. So we don't do divisions by 0. Okay, but let's just assume that for simplicity. And finally, if you see these two expressions, right, they're exactly equal on both sides, right? So this really means that I should set w to be beta. Okay, so to minimize this whole expression, even though it looked complicated in this original product, I should choose w to be beta. That's the maximum likelihood estimate. So what does this mean, right? So recall again, w was the parameter that we want to be equal to the probability of seeing a heads. And beta was the fraction of heads that we actually saw in these n examples, right? So it makes sense, right, that if I have n examples and I see a beta fraction of 1s, then of course the best I can do to guess the actual bias of the coin is to say, well, the bias is probably beta. This is a very reasonable prediction, right? So you're just going to predict that the chance of seeing a 1 is the fraction of 1s that you saw. Okay, and that is the maximum likelihood estimate. Okay, so right, if you just return to what we had before, right, the setup was really that we had these n coin tosses, and we saw a beta fraction of 1s. And if we assume that w was the probability of seeing a heads, then you could say, then you give an expression for the likelihood of the data. And then we wanted to maximize this expression by choosing w carefully. And we went through all these steps and saw that the best choice of w was to choose w to be beta. Okay. So this is really what we did along the way, was that we wanted to maximize this huge product with exponents. So we did a trick where we took negative log likelihood to turn it into a minimization problem where we don't have these exponentiations. Good. And then we saw, because negative log is a strictly decreasing function, then minimizing this new expression is the same as maximizing the original expression. And one nice thing that we observed was also, in addition to turning into a minimization problem, at least for this expression up here, it also becomes a convex function. So that also helps us, because then we can just compute the gradient and set it to 0. Okay, so let me just conclude this part of the video by just going back to linear regression that we saw in the previous videos. So in linear regression, we had the loss function here, where there's this sum of squared, right? So it was the sum over all the training examples. It's inner product between xi and w minus yi squared. So it's a function from d to r. And the strategy that we followed was to say we will compute the gradient vector, and we set it to 0. Okay, so the justification for why we did this is that it is actually possible to prove that this loss function here is a convex function of the w's. Okay, so you can try to use the definitions that we saw earlier, not the one with the second derivative, setting that to 0. That doesn't make sense. Or just testing that the second derivative is non-negative doesn't completely make sense, because this is a function of multiple variables. But there's a generalization of that rule that makes it easy to test it, but we'll not do that here. Okay, but in general, you just have to test that this is indeed a convex function of w, which then justifies the strategy of setting the gradient to 0, because that gives a global optimum. Okay, so enough with convex functions, and now in the next video we'll return to apply this framework of convex functions and so on, and negative log likelihoods to finally derive the algorithm for logistic regression.